Okay, so here we have some problems from chapter 15. And so just to highlight as we start this first problem, the 5 things that are important from chapter 15. The first is drawing structures. And I'm going to say here, previous knowledge. And what I mean by that is I mean the ability to draw Lewis structures, to be able to think about molecular shape, and to think about molecular polarity. So this was stuff that was learned in Gen Chem 1 in Chapter 10. And so I have some worksheets that'll be posted on this. The first is, again, this is information from Chem 121, which is Gen Chem 1. Worksheet 20 deals with how to draw Lewis structures. And so there's several sample problems that are in here. And importantly, at the end, there's some additional practice that goes through about 20 different structures that you can practice drawing Lewis structures with. Worksheet 21 deals with how to predict molecular shape, and so that has to do with hybridization and molecular shape. So the idea of things being linear, trigonal planar, bent, trigonal pyramidal, tetrahedral, and so forth. So again, worksheet practicing that, and then the last part of this actually says to take the molecules that are at the end of worksheet number 20 and do the same treatment in terms of molecular shape. And then thirdly is how to predict molecular polarity. So again, some sample problems working through this and then using this on those same set of 20 different molecules. So that's fairly involved from Gen Chem 1, and it deals with a lot of molecules that what we say expand their octets. With chapter 15 here, we're really dealing with octet obeying molecules. So we're really only going to be considering molecules that have carbon, oxygen, nitrogen, hydrogen within them generally. And these are the most relevant biological molecules. So again, drawing structures, I'm assuming a certain level of previous knowledge with Lewis structures, molecular shapes, polarity, and again with molecular shapes, thinking about hybridization. So sp2, sp3, hybridization, thinking about molecular shape, like is this tetrahedral, trigonal planar, bent, in that regard. Next, so that's again the first thing that's important. The next thing that's important with this chapter is a new way of thinking about drawing structures. And that, again, is what is key with this first sample problem, is learning how to draw skeletal structures. And for the most part, any structures that are going to be drawn in this chapter are going to be drawn using this skeletal structure format. So it's important that we learn how to do that well. So another worksheet that's available that I will have a video on for this is on drawing chemical structures practice. So again, taking some of these condensed structures and translating them into skeletal structures. So I'm going to assume that maybe you've seen that already as you're working through this first sample problem, or that you're fairly comfortable with it. Okay. Again, just to highlight the third, fourth, and fifth things that are important. The third thing that's kind of important in this chapter is functional groups. And so we've got additional worksheets and sample problems to work through with that. So sample problem 15.7 will work through recognizing functional groups. And then I'll also have a video on the in-class handout that we did going through identifying functional groups on a variety of different molecules. So that's the third thing. The fourth thing deals with reactivity. And for the most part, even though your textbook goes into a lot on different kinds of reactivity for organic molecules, there's 2 things that I'm focusing on. And the idea is that we recognize molecules that are nucleophilic, which we can abbreviate with NU and 2 little dots to signify a lone pair. Those are electron-rich molecules. And electrophiles, which are electron-poor molecules, which we abbreviate with an E with a little plus sign. So being able to recognize in our functional groups atoms that are nucleophilic or atoms that are electrophilic are really important. And then also with reactivity, is important to think about redox chemistry. So that's oxidation and reduction chemistry. And we went through a few problems in class with regards to that. But I want you to be able to look at a chemical reaction and tell me whether or not oxidation or reduction is happening in that chemical process. So that's what you need to know for reactivity. And lastly, the fifth thing that's important, we talk about biological molecules. And there's not a lot that we're going to do with biological molecules. It's really just applying some of the same things that we've already seen. Can you identify functional groups in those biological molecules? Can you think about their polarity? Can you think about reactivity? And we're going to talk about certain kinds of reactivity. So we don't have a specific worksheet to deal with that. Look through the notes on that section to kind of see the information that you need to know for that. All right, so that being said, we're going to work through sample problem 15.1 on drawing hydrocarbons. And so I'm going to go through kind of a systematic way of doing this, which is going to be the easiest way if you have to do problems like this. So the first part here says to draw structures that have different atom arrangements for a hydrocarbon. So when we say hydrocarbon, the only atoms that we're thinking about are carbon and hydrogen. So we'd like to draw all possible structures that have 6 carbon atoms, no multiple bonds, and no rings. So kind of a systematic way to think about doing this is let's just draw 6 carbons in a straight line. So again, I'm only going to be using our new knowledge, which is drawing things as skeletal structures. Again, assuming that you've already looked at the previous practice sheet for drawing skeletal structures, I'm going to go through this fairly quickly. Remember, when we draw skeletal structures, we want to draw them as zigzag lines because that's what tetrahedral carbon atoms look like. And so to draw them, always start by counting. As soon as you put your pencil down, say number 1, and then you say 2, 3, 4, 5, 6. Remembering that each intersection of a line or end of the line represents a carbon atom. Early on, if you want to kind of make little dots to remind yourself of that, that's okay. But here we see that there's 6 carbon atoms drawn in a line. This is going to be our simplest hydrocarbon that has 6 carbons, no multiple bonds, and no rings. So beyond that, what we want to do is move 1 carbon atom shorter and start adding branches, or what I've called dangles in class. So this again is a C6 chain. So let's make a C5 chain. So again, 1, 2, 3, 4, 5 carbon atoms. And now we want to dangle off 1 carbon atom because that's all that we have left to work with. So dangling off 1 carbon atom here, we can put it in this position. 1, 2, 3, 4, 5. We can put it in this position. If we tried to go like this and continue this systematically, this is not a new structure. Flip this guy around and you really realize that it's the same as the first one that we've drawn. So right now we have 1, 2, 3 unique structures that have 6 carbon atoms, no multiple bonds, and no rings. So let's now go to a 4 carbon chain. 1, 2, 3, 4. Now adding in 2 more dangles, we can add them on different carbon atoms. 1, 2, 3, 4, or we can add them on the same carbon atom. And that makes 2 more unique structures. Well, you might say, what if we were to draw a structure where we had something like this, and then we put those 2 carbon atoms together, like 1, 2. Isn't that a unique structure? Here's a 4 carbon chain, and then we've dangled 2 off of them. But look here, we've got 1, 2, 3, 4, 5 carbons in a chain where we've dangled 1 carbon off the middle. This is not, again, a unique structure because it's the same as this one. And this is where it's really important to be able to see whether molecules are truly what we call constitutional isomers of one another. These are all constitutional isomers, meaning in order to interconvert them, we would need to break bonds and put things back together. To interconvert this guy and this guy, I'd have to physically break this guy off and reattach him over to the other side. However, molecules like these two and these ones are really the same because they're interconvertible by rotation. They just look different in 2-dimensional space. Okay, so we'd have 1, 2, 3, 4, 5 unique structures that we could draw that are hydrocarbons with 6 carbon atoms, no multiple bonds, and no rings. So let's continue on to our next problem here. Now we'd like to have 4 carbon atoms having 1 double bond but no ring. So the easiest way, again, is to start by making 4 carbon atoms in a row. And we can make a double bond here at the end, or making 4 carbons and making a double bond in the middle. Those are going to be 2 unique structures. Continuing our theme, those are the only 2 structures we can draw with all 4 carbon atoms in a row. Let's draw 3 carbons in a row. And again, this looks kind of weird to realize that there's 3 carbons, but remember, every time there's the end of a line or the intersection of a line, that's a carbon atom. So there's 3 there. We can draw 1 carbon atom coming up, and that would be a unique kind of structural framework here where we have only 3 carbons in a row. And then we can add in our double bond. Notice that there's symmetry within this molecule, so adding the double bond at any of those positions would actually be the same thing. So going and trying to draw this and say that it's something unique, again, would not be the case. This is the same as this molecule. And those are the only 3 structures that we can draw for molecules that have 4 carbon atoms, 1 double bond, and no rings. Lastly, let's think about 4 carbon atoms, no multiple bonds, and having 1 ring. Well, the easiest structure to draw that is a closed structure, so when we say a ring structure, that really means a closed structure that has 4 atoms, is to have all 4 of those atoms connected together as a square, as a cyclobutane ring here. So that's going to be the simplest way. And again, it might be easier, particularly with this guy, if we remember that if we were to draw out all the carbon atoms, that's what that would look like. We also can draw another structure that would be a cyclopentane ring. So again, this is cyclobutane, cyclopropane. And since that only takes up 3 carbon atoms, we have room to have 1 of them dangling outside of the ring. But again, all 3 of these positions in this cyclopropane are identical for putting that external carbon atom. So again, this is drawing all possible constitutional isomers with the given conditions. I'm not likely to give you a problem like that in an exam or a quiz because there's just too many structures to draw and there's too great of a concern that you'd miss one of them. On an exam, you might see something where I tell you draw all 3 possible structures, for example, for this second one. So I tell you how many structures you're likely to see.